there are some special sequences that deserve particular attention. The first of which we'll discuss here are the factorials. N factorial. We may write 1 factorial. 1 factorial is simply 1. 2 factorial means 2 times 1, which is 2. 3 factorial means 3 times 2 times 1, which is 6. 4 factorial means 4 times 3 times 2 times 1, which is 24. And that process never terminates. What is not very challenging to see is these numbers get very big very quickly. When I write 5 factorial, this is 5 times, and what I'm going to write here, 4, 3, 2, 1, is what I've already written here before. This, I already know this is 24. Whatever 5 times 24 is, that's 120. And so you can see that multiply by 2, multiply by 3, multiply by 4, multiply by 5, multiply by 6. So if we have 1 factorial, 2 factorial, multiply the previous number by 3 is 6, times 4 is 24, times 5 is 120, times 6 is 720, times 7 is 5,040, times 8 is 32, it's 4032, it's a big number, 40320, and those numbers just get gigantically huge as that goes on. But that's the special sequence that's called the factorial. The symbol is the exclamation point, factorial. Factorial. It is convenient to be able to simplify factorials. So let's just suppose I have, let's suppose I have 8 factorial, and I'm going to divide that by, I'm going to pick a number out of the blue sky, I'm going to divide that by 5 factorial. The question is, what is that? Now you could get a calculator and calculate it out, but that defeats the purpose, and there's a particular case later on where that becomes cumbersome. So for our purposes, let's go ahead and do this computation. Now, when I write 4 factorial, this is the expanded form. But look, what I have here in the orange, 3 times 2 times 1, that is this. This in the orange is this. 3 factorial is this stuff. I could just as easily write 4 times stuff. I could write this as 4 times 3 factorial because that is this. And the point is, I can write this if I wish. I can write this as 8 times 7 times, and then just put everything else as 6 factorial. Because 8 times 7 times 6, what would this be? This 6 times 5 times 4 times 3 times 2 times 1. So you may terminate the expansion at any convenient number. You may stop 8 factorial, you get 8, then 7, then 6 factorial, and just stop there. Or if you wish, you can write this as 8 times 7 times 6 times 5 factorial. Just leave all that in the factorial. You may terminate this factorial writing whenever is convenient. It turns out it's convenient to stop it at 5. And so 8 factorial is 8 times 7 times 6 times, I'm going to stop here. 5 factorial is 5 factorial, and look, everything cancels at one swell foop. And whatever 8 times 7 times 6 is, that's not very hard to do. It's a number 56 times 6, whatever that is. So that's 8 times 42 is 16, 32, 33, I think it is, 336. Don't make me swear to that, but I think it's 336. So being able to compute these is a particular convenience for some of the work you'll be doing later on. For our purposes for now, just be able to recognize the factorials when you see them. The factorial pattern 1, 2, 6, 24, 120, 720. By then, you should be able to recognize the factorial pattern when you see it. Now, there are other factorials that come into play. Something like this. When n is 1, this is 2 factorial. Now, I shouldn't say this is equals. This generates these terms generate. So when n is 1, this is 2 factorial, which is 2. When n is 2, this is 4 factorial, which is 24. When n is 3, this is 6 factorial, which is 720. And so what this represents is every other factorial. Every other factorial. And this is already up at 40,320. And so these numbers get really big, really fast. Factorials are very often used to represent quantities that get very fast, very big, where a small change of the input corresponds to a large change on the output. So factorials get used in those, in some of the computations we'll be doing later on. Factorials come into play in some sort of surprising places. All right. There's another notion that comes into play when we're dealing with sequences, all sorts of sequences. And it's, well, let's do this. Suppose we're given a sequence. Suppose we're given a sequence. And again, I'm going to forgo using the parentheses or the braces. I will use this notation to mean this sequence is defined by that rule. The question is, does that converge? Do those terms approach a horizontal asymptote? Now, this is so simple, it's almost beyond working with, but just to show how it works. One way to show that this, so the question is, does this converge? Does that converge? Well, here's one way to find that out. Consider the associated function. See, what we're asking, if the question is, does this converge? What we're asking is, does that have a finite value? Does this approach a finite limit? Well, it might look obvious, but let's make it official here. The way we know that is because let's consider the associated function. Now, we do know, because of our work with the differential calculus, we do know the limit as x goes to infinity of 1 over x. We do know that goes to 0. And since they are the associated function of, this is the associated function of this sequence, they're associated. If this goes to 0, therefore, we know the limit as n goes to infinity of an goes to 0, and therefore it converges. In fact, we say it converges to 0. This converges to 0. If you know the number, then you know it converges. Now, very often we're not asked to find the number. All we ask is, does it or does it not converge? Now, that might seem to just cover all the bases, but here's the issue. Consider this a sequence. Let's call this Bn. 1 over n factorial. Now, the problem is, in the ordinary sense that we've studied so far, there is no associated function for that. We may not talk about this function. Again, this is for our work we're doing here. It is possible to generalize the factorial function. That is well beyond the scope of our course. So for our purposes now, it suffices to say that this function does not exist. Right? Because these are real numbers, right? Where you have to multiply every number greater than n. Well, that can be done here. If I want to say, for example, 5 factorial, I know it's 5 times 4 times 3 times 2 times 1. But here, if it's the real number 5, do you include the decimals or not? Well, no. The problem is this idea has no basis for a continuous function. And so appealing to the associated function does not help for that function, and there are others like it. So we're going to get some different tools to talk about how to determine if a sequence converges, and there are tools we're going to be able to use on that. One of the tools is something you've been exposed to before. One of the tools is the squeezing theorem. Now, you encountered the squeezing theorem way back in Calculus 1 where you're trying to establish certain limits, in particular sine of x over x. But the squeezing theorem comes into play. The squeezing theorem for sequences says this. If, and it's a big if this is the function whose behavior we want to know. This is the unknown function, or the unknown sequence. This is the sequence whose behavior we want to know. If it is captured between two others, and if an, now here's a shorthand. Limit n goes to infinity of an is equal to L. Shorthand for that is this. An goes to L. N goes to infinity, an goes to L. So this is shorthand for this larger expression. If we know an goes to L, and Cn goes to limit L, then we may say that Bn also goes to the limit of L. So if the outside functions go to the same limit value, then Bn must also go to that limit value, assuming Bn is captured between. Now, for you guys for this semester, you just need to be sort of aware of this and recognize this argument when it happens. I'm not going to have you create this argument from scratch. But I'm going to show you some logic here, and you should be able to follow me. I'm going to use this rule, this theorem, I'm going to show that this limit actually, this sequence actually goes to 0. And here's what I'm going to do. I'm going to create sequence an and sequence Cn. I'm going to establish that this is always between the two. I'm going to show that an, in this case, is going to go to 0. Cn is going to go to 0. And as soon as you do that, the squeezing theorem guarantees that the middle must also go to 0. Here's how that works. Now, I would not expect a student to be able to reproduce this. You do not need to be able to rewrite this kind of thing on exam. I'm just going to show you the style of proof that happens here. And I know to do these pieces because I've been through the course before, I've been through some higher level work, and because I've actually read the textbook. So, we do know this. Let an equal the constant sequence 0. Now, no matter what this is, now let's go back here. What are these terms? These terms are 1 over 1, 1 over 2, 1 over 6, 1 over 24, 1 over 120, 1 over 720, and so on. Now, they're tiny, but they're positive. And so we do know if we choose an to be 0, it's the constant sequence at 0, then yes, an is less than or equal to Bn for all values of n. 0 is less than all those because they're always positive. Now, another piece is this. We know, let me get rid of this. We know n is less than or equal to n factorial. 1 is less than or equal to 1. 2 is less than or equal to 2. 3 is less than or equal to 6. 4 is less than or equal to 24. It can easily be shown that n is always less than or equal to n factorial. Let me turn that around. N factorial is greater than or equal to n. Let me just turn it around, put the big one in the front. Now, it's a property of all fractions. If fraction a is less than fraction b, when you form reciprocals, fraction a is now greater than. Whenever you form reciprocals, you must reverse the direction of the inequality. That can very easily be shown. So what I'm going to do is form the reciprocal, reverse the inequality, and so 1 over n factorial is always less than or equal to 1 over n. I'm going to choose this to be sequence C. So if an is 0, we have this. If cn is 1 over n, here's bn is less than or equal to cn. So I have established that requirement. The next thing I have to show is that an goes to L, or in this case, 0, and cn goes to 0. Well, look. an is uniformly 0, cn is 1 over n. So we do have zeros less than or equal to 1 over n factorial, less than or equal to 1 over n. an, bn, cn. What is the limit of 0? The limit of a constant is the constant. So an goes to 0. What's the limit of 1 over n? Now, there is no corresponding there is no associated function for n factorial, but there is an associated function for 1 over n. And we do know that that associated function does go to 0. We have already established that this does go to 0. So cn goes to 0. And there we have it. B is captured between an and cn, both of which go to 0. Therefore, we conclude bn goes to 0. Now, that's not a particular, being able to reproduce that, and I did it in a very quick and slapdash way. But the point is this. 1 over n factorial goes to 0. 1 over n factorial goes to 0. We will use that over and over and over and over again. You don't need to be able to generate this proof, but you should be well acquainted with the final result, that 1 over n factorial goes to 0, and you should be able to recognize a squeezing theorem argument now when you see one, not just in this course, but in any course you'll encounter going up through the coursework. All right?